Good evening. So let us wait for a couple of more minutes to allow more people to join. Thank you. So, good evening, everyone. Welcome to the bonus session of the Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. We have already covered the course contents for the course, which was 12 weeks long. This is just a bonus session which will cover content which is not directly relevant to the final examination, but looks to address some of the other additional aspects of additive manufacturing, which could not be covered in the course because of time constraints. So the topics which we'll be looking into today are firstly the fundamentals of the numerical modeling of additive processes, and later also we'll look at some of the concepts and general ideas associated with the multi-metal or multi-material additive manufacturing. So the contents of the first session belong to Professor Swaroop Bagh, who is a faculty in the Department of Mechanical Engineering at IIT Guwahati. First, just a very quick recap of the additive process itself. We have been talking about it for the past 3 months, but a recap never hurts. So basically, additive manufacturing is a layer by layer manufacturing process. It starts from a digital CAD model, which is then sliced, which is first it is turned into an STL or into an approximate model. Then it is sliced. Then the pre-processing steps also involves the calculation of the support structures. Then it is passed on to the building machine or the printing machine to be printed. There, during the building, several process parameters, including the feedstock, have to be optimized to achieve the optimum part quality and part finish. And finally, there might be some post-processing steps also involved to obtain the required levels of surface finish or of, say, material homogeneity and other things. So, one of the key aspects of the definition of additive manufacturing is that there should not be any subtractive or formative methods involved. It should be wholly additive. And if you would recollect, we also looked at some of the processes such as laminated object manufacturing, which inherently has a subtractive step. So by default, all laminated object manufacturing processes are hybrid in nature. However, the very pure definition states that there should not be any subtractive methods involved. If there are, then the process stops being only additive and becomes a hybrid process. And the additive manufacturing method also leads to very effective utilization of materials. Because in the subtractive method, say we start with a larger block, then subtract or machine out the material to obtain the final part, which will only be a subset of the volume of the entire finishing block of material. Whereas going by the additive manufacturing route, we deposit material or we process material only where it is required. So the wastage is minimum. Even in cases such as, say, powder bed additive manufacturing or VAT photopolymerization, the feedstock material which can be recollected and it can be recycled. And to deal with the surface roughness aspect, definitely post processing is required. Whereas Some of the processes, such as say DLP, digital light processing, and wet photopolymerization, can produce very fine or very thin layers. They are, however, limited to a very say a very small set of materials, such as polymers. Binder jetting is very versatile in terms of materials. However, it can process materials such as polymers, metals, ceramics, or even a combination of any or all of these in the form of multi material or functionally graded materials. However, it is still limited by the layer height, which is not as fine as, say, that obtained in wet photopolymerization. So the choice of process will depend on the final requirements as well as the material which needs to be processed. And again, a key concept which is, say, revised here is that is the optimum layer, is the layer thickness chosen for this geometry optimum? And this reminds us of the concept of adaptive meshing, where in regions where we do not have great curvatures, we can opt for thicker layer heights to decrease the build time and increase the productivity. Whereas in regions where the curvature is high, we should opt for finer layer heights to preserve the geometry of the part. And additive is a process of depositing or building materials in a three-dimensional fashion by adding them one layer upon the other. And of course, it will start from a digital or a 3D CAD model. And the primary reason for the growing adoption of additive processes is because of the almost endless design flexibility which it provides. So we are not really limited by the manufacturing process itself, and we need not limit our design to the capability of our manufacturing system. In fact, we are free and truly boundless in designing whatever we want, and we now have a method to manufacture it. Further, the part count is deeply reduced. There is a very illustrative example of the LEAP engine nozzle developed by GE, which, when manufactured by the conventional route, has as many as 30 individual parts, which have to be assembled later. Whereas when processed by the additive route, it is all a single unibody. So in just one nozzle, you used to have 30 separate parts. They have to be standardized. They would have their own geometric dimensions and tolerances. They have to be interchangeable. And of course, we know that the joints are the weakest part of any design, and that is where they would have failed from. And later, we make them into a unibody. So we reduce the design effort, we reduce the part count, as well as we increase the life of this part. The lead times are reduced, as we discussed, the material wastage is also far lower. Some of the typical or the key aspects which need to be considered, especially when we are trying to, say, model any additive process, at least very rudimentarily, are the motion control, the heat source, and the type of feedstock as well as feedstock motion. So here we have a very broad classification of the additive processes based on the energy source, which in this case, say, might be a beam based or arc based. So this is for processing metals only. Of course, when you have other source feedstocks such as polymers and all, cement, the types of energy sources may still be different. And here are some illustrative schematics of the processes. In the powder bed based method specifically, such as laser powder bed fusion or in, say, binder jetting, the 3D CAD model is sliced into planar layers and the scan path is generated or the tool path is generated. Now, a very thin layer of the powder is spread over the substrate. We discussed how the powder can be made available either via a top feeding or a bottom feeding system. And by relative motion of the substrate and the top layer, a cavity is generated. Now, any powder recoating mechanism, such as a roller blade or a doctor's blade or, say, a slot feeder, can simply be used to deposit the necessary volume of powder or the required layer height of powder into the generated cavity, which will then be scanned by the laser or the energy source to print the parts in that slice. The particles can be fused either by melting or by sintering. The build chamber is often purged with purified argon or nitrogen to prevent oxidation and to prevent contamination, also to maintain the chemical composition of the parts. However, we saw that in processes such as binder jetting, this might not be necessary because the temperatures achieved are very low. and the susceptibility to oxidation thus is also lower. Further, once one of the layers is scanned, or say the part in the layer is printed, the z-axis again moves, and then a new fresh layer of powder is spread, and the process continues. Some of the key process parameters which are related to the powder bed fusion process, or can even be said which are deciding factors of any AM process in general, are the heat source, which is the heat source parts, in this case a laser power, the size of the beam. If it is a pulsed source and not a continuous one, then the pulse duration and the pulse frequency. Again, the build strategy dictates the final part quality and part properties, and that would include factors such as the scan pattern, the hatch spacing, which, if we would remember that in the case of metal inert gas or gas metal arc welding based additive processes, has been shown to be equivalent to two-thirds of the bead width. So the ideal head spacing or the pitch P was equal to two-thirds of the individual bead width for a multi-track deposition in the same plane, and this would provide the flattest surface or the best surface finish. Again, depending on the scan speed, our print characteristics will change. So if the scan speed is too high, it may lead to, say, insufficient bonding or lack of fusion types of defects. Or if the scan speed is very low, then we can have over deposition and very low production times. Again, the type of the feed material used and the effort which we put into modeling the feed material will dictate our final results. So in case it is a powder, the powder shape in terms of the sphericity will dictate the powder flowability as well as the packing. Again, the size of the powders, they will never have just one mean size of powders. There will be a distribution, and the sort of distribution is also necessary to ensure proper packing density and compaction, as we discussed. However, the distribution should not be very wide. The Yeah, we discussed about the distribution. The layer thickness which we choose will dictate the deposition times as well as the part quality. So if you opt for a very thick layers, then we'll lose out on the part geometry. However, the production times might be lower, so it might be suited to simple geometries. However, if you opt for very thin layers, while we will be able to preserve the geometry of the part and our post-processing effort would be lessened, the time taken for the print would increase greatly. As well as often the minimum layer thickness is a function of the building process itself and it cannot be controlled. The material properties have to be evaluated and fed into any numerical model, which is to simulate an additive process. And this becomes especially problematic for, say, new materials, non-standardized materials, or in the case of multiple materials, where we are not sure what properties to pick, in what ratio should they be combined, or if even a simple rule of mixture type formulation is sufficient. So we'll cover more of such aspects in the second slide for today. And there will always be some process specific parameters which need to be accounted for, such as in the case of powder bed example, the temperature, if any, used for preheating, such as in electron beam melting, we know that there are two passes. The first pass is conducted with a diffuse electron beam, which simply sinters the powder particles on the bed, does not melt them fully, and preheats them to an applicable temperature. And in the second pass, finally, the melting occurs and the particles are fused. Also, the environment, which should be vacuum in case of, say, an electron beam melting type setup, should be purged with inert gases in a powder bed fusion of any reactive metal such as aluminum or titanium, or it can be simply an open atmosphere in the case of binder jetting processes. Now, directed energy deposition, as opposed to, say, powder bed fusion, is more suitable for making large parts, as well as it has some inherently, say, better applications, or there are applications which the DED process is inherently more suited to, such as repair of critical components, because then you simply scan the part from where the part is, the area or the region from where the component is damaged, and you deposit and finish only that area rather than having to immerse the entire setup in, say, a powder bed. and having to process it. And again, the powder bed system itself is limited because of the inherent cost and build time, as well as the size of the parts will be limited by the size of the powder bed. We know that the larger powder bed we take, irrespective of the final dimension of the part itself, we have to fill the entire bed with powder for the process to take place. And for the case of the direct energy deposition type processes, the powder deposition has to be synchronized with the heat source. And the scaling up of DAD from an industrial perspective or a commercial perspective is easier as well as more cost effective. It has also been historically used for cladding, which is basically a coating operation on existing structures to improve certain surface properties such as corrosion resistance, abrasion resistance, or wear resistance. And as we were discussing, it also had the other important applications in the repair of cracks or defects in critical parts, in providing a wear resistant coating on particular areas, or to protect the specific areas of object from corrosion. However, even more than DD, for high production rates, the process of choice is actually wire arc additive manufacturing, which has been shown to have the highest deposition rates. Of course, the flip side is that because of the higher deposition rates and the thicker layers, the geometry of the parts are not as precise, or the geometric control is not as precise as some of the other processes. Here, instead of a beam, we have an electric arc which acts as the energy source. And in the case of GMO, it is established between a consumable electrode and the workpiece itself. And we also discussed the various modes of metal transfer, some of which were the globular mode, short circuiting, spray, and pulse spray. So while the globular mode had the highest deposition rate, and the spray-based or pulse spray-based process had the lowest, there were always some trade-offs, such as the spray-based processes could spray over a larger area, whereas the globular deposition was limited to smaller or more localized regions. In short circuiting, we always had, say, a very high peak or a high sharp rise in temperatures, which led to the melting and deposition of the metal droplets or the feedstock droplets. And as we discussed, GMO generally has very high deposition rates and also a high melting efficiency. However, for certain metals such as aluminum and titanium, the cold metal transfer welding has been found to be more effective, where rather than depending on the short circuiting and the very sharp rise in temperature for detachment of the metal droplet, we detach the droplet by some mechanical means, where as soon as the metal droplet is in contact with the pre-deposited bead or the substrate, backward motion is applied on the feedstock, which detaches the droplet from it without such large changes in temperature as in the case of short circuiting. That is the reason for calling it cold, because the temperatures achieved are far lower. And the difference between this and MIG welding is the type of mechanical droplet cutting method. And here, no electromagnetic forces are used for detachment. Now, moving to our main topic for discussion, which is the numerical modeling of additive processes. And it is inherently complex because of the large variety of phenomena which we must address if we want to make a very fully faithful model of the additive processes. Some of these phenomena which coexist are the melting and solidification, as well as vaporization and phase changes that take place inside the metal or inside the feedstock, the surface tension dominated free surface flow, including the effects of the Marangoni convection, the heat and mass transfer that occurs in the melt pool, which can redistribute the material or which affects the temperature profiles, the motion of the heat source itself, as well as the modeling of the free surface, which is in contact with the atmosphere. And the goal for using an effective numerical method or the effective numerical model is to actually assess the impact of process parameters and predict the optimized conditions without doing a large number of trials. So, as we are already aware in the current technological landscape, the additive machines have a significant capital cost for their establishment, as well as the running costs can be very high, and even the feedstock is costly, as well as other consumables such as say the nozzles which are used for deposition also have very short lives. This is in addition to the lasing system itself, which is very sophisticated and costly. Thus, performing a large number of experimental trials to obtain the optimized conditions via trial and error is not really very, say, economic. Thus, it would be better if you are able to develop a computational model of the process which is faithful enough to give us some useful inferences and can actually prevent the need for performing a large number of trial and error experiments. Secondly, and perhaps more importantly, there are certain uh, aspects of information which can only be, say, extracted from a numerical model and are not so readily available or cannot be so easily tracked from the experiment itself, such as the temperature profiles or the temperature isocontours. While we can image the area with some thermal cameras and try to generate some, say, the thermal images, however, they will not be, say, as accurate or even as easy to acquire as via some uh, faithful model of the process. Then there are the transport phenomena, such as the heat transfer and the fluid dynamics, the buoyancy-driven flow, the Marangoni convection, and the flow of temperature and species gradients, which will in turn affect the mechanical and microstructural properties. So any model which hopes to predict the mechanical properties of the finished parts must take these phenomena into account and should model them. Again, the surface tension driven free surface flow determines the final surface and smoothness of the clad. So the final geometry of the deposited bead or the geometry of the part will be decided by certain inherent factors, and these are especially helpful or useful in the cases where we're trying to predict part distortion or the final part geometry or even residual stresses. The solidification of alloys becomes especially important at the mushy region between which has a mixture of the liquid and solidified phases, and the transport phenomena may be seen to occur across a wide range of time and length scales. This has given rise to a need for multi-scale modeling methods. So you have certain phenomena which are very fast and occurring in say some microseconds or nanoseconds. You have other phenomena which take a lot of time and say are occurring at the scale of certain seconds or milliseconds. So these scales are not directly comparable, and the processes have to be simulated independently and then later combined via an ensemble type of model. And thus, we are actually modeling the same process but at various scales to find out the various useful sets of information. The evolution of the interface between the different phases or between the different microstructural constituents are again coupled with the physical fields such as the temperature, the flow, velocities, and the concentration. And some of the approaches which have been successfully utilized for the modeling of additive processes are the phase field method, certain front tracking methods, then there are the immersed boundary methods and the level set methods. And these methods are usually useful for very small domains. So you cannot really do, say, part scale simulations. With time, they are becoming possible, but even till now, even recently, they are not really the standard and are very difficult to perform. And these are still on the continuum scale, usually ranging between, say, zero point 0.1 micron to 10 millimeter. Of course, the other type of simulation are at the atomistic scale, which actually study the interactions between molecules or atoms and tries to come up with certain important information or properties which dictate the particle behavior or the material behavior at the microscopic or the mesoscopic level. Now, one way to do the numerical analysis of additive process, since it involves both thermal loads and mechanical stresses, is to decouple them and perform them sequentially. So one of the approaches is to actually perform the thermal analysis independently of the mechanical analysis. And the reasoning for this is because the change in the thermal boundary conditions, because of the deformation, is negligible. and does not appreciably affect the results. And again, the second reason can be that the plastic strain energy during deformation is significantly small compared to the input energy itself. So by neglecting or ignoring this energy, our final results will not be very erroneous or much further from the mark. And this type of analysis is usually referred to as a weakly coupled analysis because the two phenomena are decoupled or at least were not very strongly coupled. And first, the thermal history is obtained or the thermal isocontours or profiles are obtained, which are then used as an input to the quasi-static stress analysis. However, we are very well aware that most of the material properties, such as say the coefficient of thermal expansion or even the density, actually vary as a function of temperature. And that too, they are not very linear. And these things have to be taken into account while developing a model. So rather than say feeding the constant density as 8 gram per cc for stainless steel 316L, we actually have to feed the temperature dependent density function, which will then give us a more accurate or a more faithful recreation of the process. Now, several numerical techniques have been successfully used, some of which you might be already aware of, such as the finite element method, the finite difference method, and especially for formulating or for say simulating the flow types, the finite volume method. And in additive components, you always have distortions or residual stresses. Again, one of the analogies between the warm process and the multi-pass welding process. So maybe a simulation which has already been developed or a model which is already very well representing the multi-pass welding process can maybe simply extend it to process such as warm. And one of the very general approaches is to use the finite element methods for recreation of the the weakly coupled thermomechanical analysis. And you will find multiple examples of the internet or in published literature where many commercial software packages such as Abacus and ANSYS have been used for these purposes. And in such cases, the heat transfer from the arc to the molten pool is actually simulated using a heat source model. So rather than considering the flux of the heat energy directly onto the deposited material, we actually account for it using a heat source model, and we'll discuss more about it in the coming slides. And this actually prescribes the heat generation per unit volume into the molten pool region, and the material deposition is actually accomplished by the activating of specific elements and depending on the controlling function. So it's not like we are actually actively depositing any materials on into the melt pool. Uh, a more likely or a more closer explanation is that the material is already there. We have simply turned it to the off state, and when our laser or the heat source reaches it, the temperature increases. And say in cases where the temperature is used as the activation function beyond a certain threshold, we will simply activate that element, and then it will be as if that element has been deposited. Of course, there are other methods which actively track the particle dynamics, such as ray tracing, in case you want to actually model or account for the interaction between the incoming particle and the already deposited melt pool. Of course, such models would be computationally very expensive. And the key thing to realize is that the type of model or the amount of approximations of phenomena you're studying uh, are always, say, a function of the end goal or the problem that you're trying to analyze. So not all processes or not all phenomena may be equally important, and the scaling analysis has to be performed to actually realize which are the phenomena you would like to consider in your model. Again, for the motion of the heat source, its path may either be linear or it can be along any random curve. And a complex, or let us say an accurate numerical model will actually address most aspects that we discussed, such as it will predict the temperature distribution at the end of each pass or during a pass. It will predict the shape and size of the molten zone as well as the heat affected zone. It will give you some idea of the solidification time, and it will account for the mass addition to the solution domain. Again, a faithful model will also emulate the fluid flow of the molten materials, and such feature will actually enhance the calculation based on temperature distributions. Of course, because of the concentration of the materials involved. Say if you are using a multi-material, if you're trying to model a multi-material deposition process, then their concentration will actually vary within the melt pool because of the flow effects. And a process which actually simulates these changes in distribution will be more faithful and more accurate in terms of corroborating with the actual experimental results. Again, the certain processes may be material specific, as we know that in the case of welding, depending on the content of sulfur on the surface, the type of melt pool generated changes. So below, say, a specific concentration, say 50 parts per million of sulfur, the melt pools are of one morphology or one type, say shallow. Whereas once the concentration of sulfur crosses some 50 parts per million, the melt pool becomes very deep. Thus, such surface active elements, if present, will significantly change the melt pool shape and size, and their effect has to be taken into account. Again, when we are talking about the final part geometries or the final build geometries, the residual stresses and the distortion that they cause should also be accounted for because they will tell us what the final geometry is like. Now, in any transient thermal analysis, the energy balance equation is solved over the entire volume of the domain, and this equation is given as shown here: rho Cp d temperature over dt, which is the variation of temperature with time, is negative of the gradient of the heat flux plus the internal heat generation. And it is through this heat generation term that we actually introduce the energy flux from our energy source. Capital T is the temperature variable, small t is the time variable, and the other coefficients are described here, such as the material density, Cp is the specific heat, and K is the temperature dependent thermal conductivity. Again, the key to notice is that this is a temperature dependent property and is also provided as such rather than choosing a fixed constant value. And when trying to model an additive process, the heat source is actually modeled, say either as a surface model or as a volumetric heat source. And depending on the approximations that are taken at this stage, our final results will vary. And the surfaces of the substrate and the evolving surface will lose heat to the surrounding environment via convection and radiation, and such effects have to be taken into account. So radiation till now has not really been incorporated very well in most of the numerical models of additive manufacturing. However, convection has been well studied, and though computationally very expensive and challenging, people have successfully demonstrated the incorporation of convective effects. Such as in the example here, where we have a surface domain and say we want to model the heat flux that is flowing into and flowing out of the surface. The initial condition we modeled as the temperature over the entire domain is equal to some T naught, and the heat flux can be given as the heat loss due to convection. So H is the convective heat transfer coefficient times T minus T infinity. And the second term can actually relate to the radiation heat loss. And the value of the heat transfer is generally assumed to be constant over the entire surface. And in the model where you actually want to skip convective heat transfer, or where it is too computationally expensive or challenging to model convection, another way to account for the heat transfer by convection is to simply use, say, a much higher value of the conduction heat transfer coefficient to account for the heat transfer by convection, but by while neglecting the fluid flow. And a very commonly used model for the heat source or the volumetric heat source is actually the Goldach's double ellipsoidal model. So you can read more about it from existing literature. This has been in use since, say, the late 1970s or early 80s. And while this is a good approximation, more realistic heat flow distribution may need to be implemented, especially for the filler material. And a way to do it is that we actually choose different power distributions across the base material and the filler material. So say you have a pre-deposited layer in which a melt pool is getting formed, and on top of it, you're also depositing some material. So what we can do is maybe we can have one sort of energy distribution or temperature distribution for the molten region into the substrate, and we can have maybe a second type of energy distribution for the deposited bead to make a more, say, accurate model. So we distribute the power between the filler and the base materials, and one part is delivered to the base material, and for this we use the Goldak's double ellipsoidal model. For the material, we may also have some uniform distribution or a distribution with a constant pattern. And this actually has been shown to and capture this very steep temperature gradients inside the melt pools, and to ensure that the correct amount of heat is delivered to the filler material elements. And as we discussed, that rather than considering the heat flux from the energy source, actually the internal heat generation term is applied to the filler finite element, the elements, and usually the centroids are tracked. And if the centroid lies within our control volume, which is usually say cubic or cuboidal, then the internal heat generation source term is applied to them to simulate the action of the energy source on these elements. And the heat generation per unit volume may actually be defined as the ratio between the wire melting power and the volume of the elements currently heated by the power source. Now, as we were discussing, the deposition of material is not really, say, it's not a common practice to really model the deposition of the materials directly. Rather, what we resort to is an element activation technique. So, say this is a substrate, and on top, what we have done is we have already said this is the final geometry that we are willing to deposit, and say it is distributed across a few layers, say in this case, 4 layers. So, what we have done is the geometry already exists, and say this will be deposited in certain fixed intervals or in certain steps. So say in one time step you have deposited only this much material. In the next time step you go for the next set and so on. So what we do is we have already the materials or the elements are already present over the region. The simple thing we do is initially they're all quiet or inactivated, and depending on the motion of the energy source, say if the laser beam is traversing, based on the motion of the energy source, we simply activate these elements one by one. So in this case, only element 1 will be active. Once the laser source has moved till here, elements 1, 2, and 3 will be active, and so on. Once this entire pass over the region has been completed, all the elements in this first layer will be active. However, the next three layers, while also present in the domain, are simply inactivated. And this has been described in this slide. So we actually resort to some element activation techniques to simulate the material deposition. The two approaches are the inactive element method and the quiet element. Of that, the quiet element method is described here, and where the filler element methods, the filler elements are already present throughout the simulation or throughout our solution domain, but they are initially assigned some quiet values in order to minimize their influence on the component behavior. And then these material properties are progressively switched from quiet to active according to the deposition process or the movement of the energy source. So usually one of the activation functions which can decide this is a temperature dependent function. So once the temperature in a certain region or in a certain, say, incremental volume or incremental element reaches the crosses the threshold temperature, we can activate the material in there, and then the material properties of that element can contribute to the overall process. And one of the simple formulations for computing these material properties are then, say, where phi is any material property, or and the gamma will be the activating function. So the overall material property phi as a function of t will actually be the sum of gamma as a function of t times phi a as a function of t, which is material property of, say, the materials in the element 1, plus 1 minus gamma t times phi q, where phi q can be the material property of the adjoining on the next element. So by using a rule of mixture type formulation, depending on the activation function, which in certain cases is decided by temperature, we can actually account for all the material properties. Again, some of the other considerations are shown here. So the amount of heat absorbed by the system is not only the heat that is getting, say, transferred by the energy source or the substrate or the pre-built layers, but also the energy that the molten pool, that is the molten droplets or the molten material carries to the surface. And of course, within the melt pool, we have convective heat transfer, and it should be considered for accurate thermal field predictions. As we discussed, the around this is that you choose a sufficiently high value for the conductive heat transfer coefficient, and then you account for this convective heat transfer coefficient heat transfer as well, without really going into the complications of the fluid flow. And the reason we would want to avoid them is because the convective transfer models are computationally very expensive as well as very challenging to design. And yeah, very high thermal conductivities are assigned in the melting temperature to compensate for the increased heat transfer in the melt pool due to Marangoni convection. So Marangoni convection is basically a surface tension driven fluid flow. So along the top surface of the melt pool, what will happen is, as we are aware, so in the center of the melt pool, the temperatures will be the highest, whereas the temperatures will be low around the periphery of the melt pool. And as you are well aware, surface tension as a function of temperature decreases with a rise in temperature. So the surface tension of the liquid will be the least in the center, where the regions are the hottest, and the surface tension will be highest around the periphery, where the temperatures are low. And because of this difference in surface tension, certain forces will be exerted on the free fluid surface, leading to convection from the center outwards towards the periphery. The normal or the natural convection or the buoyancy driven flow will have different characteristics, and it is actually the interplay between the Marangoni convection, the buoyancy driven flow, and the natural convection which finally decides the heat, temperature, and material distribution. So here are certain formulation for the conservation of the thermal energy, some of the boundary conditions, and also how we can actually divide a domain if it is symmetric into half domains and then solve for only half of the solution domain to obtain the solution for the entire system. And also it has been shown that how we can use an effective heat transfer coefficient to cover both the convective as well as the radiative heat transfer with just a single term. So we would have to perform discretization of the solution domain, both in the spatial frame as well as the temporal frame. So we have already divided the region of interest, say it is a 2D surface or a 3D volume, into finite space steps, say into some very infinitesimal cubes, or in case of surfaces, infinitesimal areas, or in case of, say, lengths, into infinitesimally small elements. And then later in the temporal space, we also have to break them into time increments. And so a very generalized formulation is shown here, which is called the alpha method for time discretization. And it's a one-step method. So here you have the entire equation. And depending on the value of alpha, which will be dictated by the choice of the scheme that we are using, we can achieve different levels of approximation. Of course, each of this scheme comes with its own set of advantages and disadvantages. Say one might be very easy to implement, but not very accurate. The other might be accurate, but it might be computationally very expensive. Or there might be certain situations in which each of these schemes are, say, prone to errors or prone to, say, very high fluctuations. So in the scenario where you have alpha equals 0, it's called the explicit Euler scheme or the forward difference scheme. Similarly, for alpha equals 1, the scheme will become an implicit Euler or a backward difference scheme. So we see that depending on the value of alpha here, if alpha is 0, this term goes to 0, whereas the other term remains 1. If alpha equals 1, this second term goes to 0, whereas the first term remains 1. Similarly here, and so on. And here, the subscripts actually refer to the discretization in the spatial domain, and the superscripts such as 1 and 2 will refer to the discretization in the temporal space. So Ti2 minus Ti1 actually refers to the, say it can refer to the difference in temperature at node I between time step 2 and time step 1, and so on. So for some of the other later developed schemes or more accurate numerical schemes such as the Crank-Nicolson, you have alpha equals half, whereas for the choice of Galerkin method, alpha is prescribed to be equal to 2 by 3. And the functions in such cases are independent of the state of time in explicit schemes. However, you can also use some pseudo steady state schemes. And in the case of welding, this may be formulated as the welding velocity in the frame of moving coordinate system can be expressed in terms of the velocity of welding, the time, and the fixed coordinate system. So these are the important factors which need to be, say, taken into account for the representation of the heat source. Among them are the nature or the type of heat source, whether it is an arc or a laser or an electron beam. This will decide, say, the size of the energy source and their characteristics. Again, the representation of the source itself, whether we are representing it as an ideal point source, as a line source, or as a distributed source with the distribution of energy. Again, in case we are choosing to go with a distributed heat source, it can either be a volumetric heat source or a surface heat source. And the surface heat source will most likely have a Gaussian distribution. Of course, other distributions have also been tested and proposed, and they may be specially suited to some special situations. However, in most of the usual cases, the Gaussian distribution proves to be good enough, and simulations performed using the Gaussian distribution are in good agreement with the experimental results. In case of the volumetric heat sources, we need also the geometric shape along with the distribution, and the movement of the heat source or the relative motion between the substrate and the heat source may be non-symmetric in terms of the geometry or even in terms of the distribution if you are opting for a non-symmetric distribution of the energy. So rather than solving just the heat transfer, we can also solve for both the heat transfer and the mass transfer, and which will then become the case of solving the transport equations. So primarily they are the conservation of mass, the conservation of momentum, and the conservation of energy. And those equations are shown here. And by proper application of the boundary conditions around each of the surfaces and by conserving these quantities, along with certain necessary assumptions such as the no slip boundary condition between the solid liquid interface in the mushy zone, as well as for a symmetric surface or a symmetric domain. Any, say, if we divide the domain into two and solve for only half of the domain, we can assume zero flux along the, say, the surface of symmetry. And till now, we have talked about developing numerical models or what are the fundamental steps needed for the development of such models. But say once you have developed a model or you have are in the first iteration of a model and you want to actually check how accurate it is, how valid are its predictions, how do we accomplish that? Which are the easily measurable quantities from an experiment that can be actually used to validate the transient nature of the information predicted by the models? So one of the uh, commonly implemented techniques is to actually match the thermal cycles. So here to the left, you see the thermal cycles for such an AM process. And I also discussed somewhat about this in one of my slides, where I explicitly calculated the thermal cycles using the ANSYS additive package, and we saw how they vary. So the location of choosing these thermal cycles is fixed, and we try to corroborate the information that is obtained from the simulation, which in this case is the black curve, and from the experiment, which in this case is the green curve. And this might also be useful in gauging whether any remelting has occurred or not. Say the melting temperature is somewhat around 275. Then we can see that in the first spike, the temperature reached some 400 degrees Celsius. And in some subsequent deposition step, it again crossed 275 degrees and reached almost 300 degrees Celsius. It can be easily gauge that some remelting has occurred. Again, the stress has also been plotted in the curve to the right, and this longitudinal stress is along a center line perpendicular to the deposition line. And here we see that between the start and 200 seconds of cooling time, how the stresses are evolving. So once we validate our model using any one of these metrics, say we validate it with the thermal cycles, we can now be assured that our model is predicting okay results and can be used for other predictions, which need not be thermal based only. So we might have validated it just for the temperatures, but because all of the physical phenomena that we are studying are interrelated, so it can be assumed that the other predictions will also be reasonably accurate. Now the next aspect is actually surface modeling of the free surface, which is the molten surface of the melt pool and is in contact with the surrounding atmosphere. And the methods to actually model this free surface are of two broad types. One is the interface tracking methods. The other is the interface capturing techniques. And for this category of problems, the common interactions to consider are the fluid particle interaction, the fluid object interaction, as well as the fluid structure interactions, the free surface and the two fluid flows, and flows with moving mechanical components. And as you can guess, these problems are computationally very challenging to implement and often may only be, say, valid for a constrained set of conditions, not generally valid. And the primary difference between the two types of techniques is also illustrated here. So the interface tracking technique actually requires meshes that track the very interfaces and are updated as the flow evolves. So we are not really having fixed meshes. The meshes are constantly evolving. Or the other way to do it is to actually opt for a mesh-free scheme, such as the smooth particle hydrodynamics. And here the positions of the mesh nodes are tracked in a Lagrangian fashion. So we know that the difference between the Lagrangian approach and the Eulerian approach is that in the Lagrangian approach, we are tracking the evolution or the trajectory of one packet of fluid as it is flowing. And it can be similar to, say, watching or traveling in a boat along the river, and we are describing or we are recording our position. The other approach, which is the Eulerian approach, which is used in the interface capturing techniques, actually fixes the area of observation or the volume of observation, and we see how the flow is occurring past that area of observation. So it's like we are sitting on the river bank and we are seeing how the boat is moving past us. Both of these techniques can be interrelated and each offers its own advantages. So in the interface tracking techniques, the Lagrangian technique is adopted, or the Lagrangian approach is more valid. And in this case, the imposition of boundary conditions at the interface is very easy, as the nodes lie on the boundary itself. Every time the interface changes, the mesh is updated or remeshing is performed, and every time the nodes will lie on the boundary itself. So we can apply the boundary conditions directly at the nodes without any need for further considerations. However, what this would mean is that because of the need to remesh or to update the meshes, there will be significant time between the steps, as well as severe computational cost. The other type of methods, which are the interface capturing methods, especially used for two fluid flows, use the fixed spatial domains and the fixed meshes. And it is just that the interface function, which demarcates the location of the interface, is computed to capture the interface. So say you already have your well-defined domain, and you have, say, an interface. So some of these regions are lying completely inside within the interface. The others are lying partially in it. And again, further these are some of the ones which are not inside the volume of the fluid. And depending on what fraction of the uh, element or the elemental cell or the unit cell is within the interface, it can have a value of the activation function, and thus we can capture the interface in a sense. Of course, this is based on the earlier description of fluid flow. So some of the commonly used interface tracking methods are the particle methods, such as the smooth particle hydrodynamics. Then there are the volume of fluid methods. There's a level set method, as well as the phase field method may also share some features with these interface tracking methods. Another technique, which is basically the development or the extension of the finite element technique itself, also called the XFEM or the extended finite element method, has been successfully used mostly for tracking, say, cracks or defects that evolve in a material. And this is based on the generalized finite element method and the partition of unity method. So if you want to read more about these methods in depth, kindly refer to the standard textbooks or internet resources. The XFEM method is especially powerful for discontinuous problems in mechanics, such as crack growth and propagation, complex fluids, interfaces, and so on. And the method is actually independent of the internal geometry and the physical interfaces. And the meshing and remeshing difficulties of discontinuous problems are overcome. So we're discussing how, say, for interface tracking methods, the mesh has to be constantly updated and the elements have to be remeshed in order to track the interface. However, in the XFEM method, this difficulty for remeshing and the computational time and cost is overcome. The discontinuous field is entirely independent of the mesh, and the enriched elements, or that is the elements or the nodes which are seeing the most action or which are most important for our consideration, are have additional degrees of freedom at the crack surface and the crack tips. And they have been used not only for the simulation of cracks, but also heterogeneous materials with voids and inclusions. So here is an example of the XFEM setup where these encircles or O's denote the over-enriched node. The enriched nodes or the nodes which are in close proximity to the feature of interest. We see that here there are certain other nodes, but they are not really enriched. However, the ones which are close to the interface or to the region of interest are enriched. So these enriched rows would have some additional integration points, and there would be some polynomial integrants based on the numerical scheme of Gauss quadrature, which most of us would be familiar with. And the ordinary Gauss rule does not really accurately capture the integration of such enriched nodes, and thus we provide them with some additional integration points and subdivide the enriched elements and also increase the integration points. In the second case, we have a crack which is getting tracked by the extended finite element method, and we see how some of the nodes are enriched compared to the others in a domain. Here is a finite element based simulation example of the wire arc additive manufacturing process, and this is the symmetric axis. So we may think that the proposer or the author only simulated for half of the domain, and because of the symmetry, the results could be applied to the entire domain. And here we have chosen certain points and with their coordinates such as G1, G2, G3, and G4. And based on the position of these points, we see that the temperature profiles obtained are different. So to correlate with an experiment, say we can weld the thermocouple wires at these locations, say at G1, at G2, and G3 and G4, and we can corroborate the temperature profiles with the simulations. And we see that depending on the location of the point chosen, the thermal cycles are different. And depending on the type of information that we seek, we must make this choice. Also, in certain cases, the Wire may also be somehow placed in between the layers such that we can study the effect of thermal cycling on the build itself rather than on just the substrate. So for the finite element modeling of additive manufacturing, the consideration of the non-uniform expansion contraction of the material, which leads to thermal cycles and consequently the residual stresses and distortions has to be taken into account. Again, the control of such residual stresses and distortions is highly important because we want to preserve the geometry of the finished part as well as prevent damage to the machines. And some of the most commonly used techniques have the sequential coupling between the transient finite element models and a moving heat source. The element birth technique or the element activation technique is used for simulating the addition of material. And the transient aspect and the highly nonlinear material behavior actually results in long computational time and high computational cost. For the mechanical analysis, which is necessary for the computation of the residual stresses and distortions, some of the governing equations are shown here, such as the mechanical stress equilibrium equation, the constitutive equation for stress and strain. Here, the strain is assumed to be consisting of all the various strains, such as the elastic component, the plastic component, the thermal component, as well as the strains introduced by transformation. And all of these combined may then be used in conjunction with the material stiffness tensor for calculating the state of stress. And here we see an example of the phase transformation induced stresses in the case of martensitic formation. And the solid state phase transformation have been reported to alter the residual stress because of thermal processing. And it is necessary to consider them for the mechanical analysis of those alloys in which such effects are significant. Here we see how during the heating and cooling cycle, the volume change is very significant as the change in temperature. And the temperature history obtained from thermal analysis in a weakly coupled system may act as the input for the structural analysis as something of a thermal load. The thermal load is divided into several load steps. So all of these simulations are incremental. They are not one-step simulations. So for very small stress steps, we calculate the for very small strain steps, we calculate the stresses, and then these stresses act as the input for the next step. Again, we calculate the strains and how the stresses are evolving, and so on and so forth. So these are performed in very fine increments, and it's not like it's a one-step process where we simply start our simulation and it directly gives us the final distribution of stresses. Again, just like most other finite element based formulations, here also we have that stiffness matrix analogy. And with the application of the necessary boundary conditions, the displacement field can be calculated. The nodal displacements are calculated, and then the displacements are further converted into the strains using the strain displacement matrix denoted by B. And depending on the type of deformation, the type of loading, whether the material is in the elastic domain or has crossed over to the plastic loading domain or the plastic deformation domain, we have to accurately use either the elastoplastic matrix or the elastic matrix only. So we determine the effective stress and compare it with the yield stress in each load step to determine whether the region is of an elastic yielding or plastic yielding. Then the load steps is applied in incremental modes of suitably small increments. And finally, when all the load steps have been applied, we determine the total plastic stress and total plastic strain. And according to the Prandtl-Royce flow rule, the incremental plastic strain is proportional to the corresponding deviatoric stresses. And here we have the implementation of the formulation of the stresses and strains. So the total incremental strain is calculated as the sum of the elastic, the plastic, and the thermal strains, as well as some phase transformation induced strains can also be included in this formulation. Then we calculate the incremental stress using the elasticity matrix, the local slope of the stress versus plastic strain, the deviatoric stress components, and the von Mises yield criteria in conjunction with the Prandtl-Roy's flow rule. The solution strategy for the stress analysis models is actually given here. So the fully coupled thermomechanical analysis can be performed where the stress analysis depends on temperature distribution and the temperature distribution itself in turn depends on the stress state. The thermal and mechanical analysis is performed simultaneously for each step, and thus we divide the total say solution time into small steps or time increments. For each time increment, we calculate the thermal field and then the mechanical field or the stress field before progressing to the next time increment. However, in sequentially coupled analysis, the entire temperature field is predefined and calculated to be used as an input to the stress calculation function, and the temperature analysis does not appreciably change the stress analysis results. So here are some further examples of the finite element based simulations of the wire arc additive manufacturing process. Here we see that some adaptive meshing has been performed. And in our regions of interest or in regions where the material is being deposited, we have opted for a very fine step size. Whereas in regions far away, we have opted for coarser mesh sizes. And this, the figure on the right shows the residual stresses at the end of the deposition cycle. Here we have the color-coded residual stresses at the end of the deposition of the first, second, third, and fourth layers. So we can see how the residual stresses are evolving. Such a measurement, especially in situ, is simply impossible from experimental means, and there's the need for numerical models and even say simple analytical models. And in more recent times, the machine learning based models is on the rise. Again, for direct material deposition, sometimes it may also become necessary to model or capture the particle and energy beam interaction. Say in the case where we are modeling or tracking the path of two particles. So this is the path of particle 2 and this one is the path of particle 1. We see that as per the temperature profiles, particle 1 never reached the melting point, which in this case is around some 1800 degrees Kelvin, 1800 Kelvin. And thus, this may be inferred to be because of the very low interaction time of the particle with the laser. And again, if we remember, the there's a higher chance of unmelted particles or partially melted particles remaining near the periphery of the melt pool compared to the center, where the particles are uh, more probable to be fully melted. This can be seen for particle 2, which has a long enough or sufficient time to interact with the energy source, and thus not only does it reach the melting point at which it faced its phase transforms from solid to liquid, it also gains certain degree of superheat, which it then transfers as say excess energy to the substrate. And here are the cases illustrated where when the particle is exactly interacting with the laser, it may not melt immediately and may need some time. It needs some finite time to reach the melting point. However, because of the very fast motion speeds of the particle, by the time it reaches the melting point, the particle may have already reached the substrate material or the energy source may have moved away and it might have started solidifying already. The particle velocity may be as high as 5 meters per second. Thus, we can see that modeling the particle and energy interaction may often turn out to be useful or important for the application. Again, this interaction may also be necessary if you want to model the exact or the accurate bead shape and size and the bead geometry. So in cases where the final finished geometry is of critical importance, we need to have a very important representation or accurate recreation of each deposited bead. And in summary, the heat transfer and solidification behavior have to be incorporated into any accurate numerical model of the additive process. The stress analysis, including volumetric dilation, has to be performed for the calculation of the residual stresses and the part distortions. Material flow analysis is important to gauge the concentration distribution, the material redistribution, as well as the actual heat transfer. Again, whether the heat transfer is occurring only by conduction or where some keyhole mode heat transfer is also occurring needs to be taken into account because it will lead to certain defects such as keyhole porosity, which have a totally different mechanism. The free surface profile is challenging to model, and the interface capturing and interface tracking techniques may prove useful in such cases. The flow behavior of the shielding gas in DMD may also provide some additional challenges, such as we already discussed. It may lead to some waviness or it may lead to turbulence of the free surface. The finite element technique is efficient and has been successfully used for these purposes. And if you want to model the microstructure or we want to make some inferences at the microstructure level, we have to opt for a multi-scale modeling approach. So that was it for this set of slides. Let us take a short break and we will resume in 10 minutes. So let us resume. In the second set of slides, I would just like to cover some of the broad aspects of multi-material additive manufacturing, or in this case, the multi-metal additive manufacturing. So first of all, we know that the multi-material additive manufacturing, or the additive manufacturing of functionally graded materials, is actually a nature-inspired concept or something borrowed from natural objects and natural creatures. Some of the examples which we have already seen previously in our slides are the functionalization of the bone density in the human body, where you have the soft collagen with hard minerals and which act together to dissipate energy. Or in certain insects, you have the legs avoiding failure due to a chitin protein matrix. And similarly, in other living matter, such as in tortoises, you have a soft body, however, you have a hard shell which resists cracking and can carry loads. For geckos, the legs have structures which make it easy climber. Similarly, for the case of engineering materials also, we may combine certain aspects of different materials into a composite to give it some functionalized behavior, such as we may have polymer, metal, or ceramic materials. And by combining any of these, we will end up with the functionally graded materials. We may also have some uh, bi or dual materials such as metal ceramic, or polymer ceramics. And another industrial need, which is often cited, is say in the case of high temperature applications, such as inside the combustion chamber of a gas turbine. So as we see that some of the regions depicted in red here are the hottest, and the parts in this region are subjected to the highest temperatures. However, some of the other regions are not so hot, such as the ones in yellow over here. And does it make sense to actually use the some additional say coating or some harder or more or a material which has better say hot hardness or high temperature performance in the hottest regions, whereas in other regions we can use materials which are structurally still resilient but say are more cost effective or are easier to process or machine. Say in the combustion chamber, on the hottest regions of the combustion chamber, we can have parts made out of Inconel, whereas in some of the other regions they may be made out of stainless steel. And the key thing would be to avoid any joints or any sudden sharp discontinuity in the material combination or the material gradation from steel to Inconel, as that would be the site of all defects or failures. And that is where the functionally graded materials come in. Similarly, another example shown here is of a geared tooth, where you have two grades of steel. So one is the inner one can be softer or say more economical. The outer layering or the outer casing can be harder, which prevents the surface defects such as pitting and abrasion. And on the right again, you have an engine section where you want to increase the heat conduction in the highly stressed area. So by and we also want to improve the temperature control in the injection nozzle for enhanced engine performance. So you have the inlet made up of copper, the nozzle body made up of steel, and the use of this copper inside this mostly steel body actually increases the heat conduction in that region because it is also the hottest. So this has also been used in this injection nozzle for large bore engines. Here are some of the other examples. Here you have a nickel and copper combustion chamber where the nickel provides the high temperature performance and the high temperature mechanical properties, whereas the copper enhances the transfer of heat away from the section. Here we have a stainless steel and inconel heat exchanger. And on the right, we also have some multi-metal lattice structures where we have, say, discrete regions of each material which are joined seamlessly with each other. And depending on the direction along which this material is loaded, it might exhibit some unique properties which are not commonly observable or cannot be achieved with just a monomaterial. However, in multi-material AM, there are often regions of, say, inhomogeneity or regions of defects, or there would be the variation in the composition of the materials or concentration of materials across the interfaces mostly, such as here in the case of a TC4 and steel joint, we have an Fe ridge zone given in yellow and a Ti ridge zone shown in gray. Again, between a TC4 and steel joint, we may also use some interlayers of vanadium and copper, which may actually help to reduce the incidence of formation of deleterious intermetallics. Here on the right, we see that between the Cu and Al interface, certain cracks have propagated and which may lead to premature defects and premature failure. So for the design of these multi-material structures, there can be certain approaches. Say for joining the two metals or alloys from 100% A, or you have 100% metal A or 100% alloy A to 100% B, we can adopt any of the three approaches. One is a direct joining between the two, that is, we directly deposit, say, material B on top of material A, and this can be done if they are metallurgically compatible and they form a very strong joint or a strong metallurgical bond. The other can be a gradient path where we progressively vary the amount of materials. Say in this case, you have 100% A over here and 0% B. And starting here, you have 100% B and 0% A. And say in between, you can have some steps of say 20% increments or so on. So here in the first step, you would have 20%, 80% A and 20% B. And some time down, you would have 40 A and 60 B and so on and so forth. And the third approach can be actually to use an intermediate section. So this material is something which has to be metallurgically compatible with both A and B, and it is usually used to prevent the direct mixing of the materials or direct joining between A and B, which might then lead to some formation of intermetallics or other brittle deleterious phases. And for the computer-aided process planning, we first identify the functional and technical requirements. Then we choose the primary material, which will be the base material from the material database. Then we choose the multi-material additive manufacturing process selection through the process database. That is to choose which processes, what processing conditions and techniques we'll be using to finally process this material or to generate the final part. Then the material composition and the part geometry are designed, and the design proposal is forwarded. Again, another aspect of design is actually allocating the material properties or assigning the material properties. So in certain cases where we want, say, a functionally graded material of this type, where certain sections are made up of copper and the rest are made up of, say, tool steel. So the brown or red ones are copper and the gray one is tool steel. So it might not be very easy to directly assign the material properties over local regions in existing software packages. The way to sidestep this is to actually split the total model into two uh, distinct parts. So you have a final part volume which has both tool steel and copper in between. So you make submodels. So you have submodel for material 1, which is tool steel. You have submodel for material 2, which in this case is copper. And here we see some in between transition state where the material mixing is taking place in between. And you end up with a final build part, which looks something like this. And what the advantage this offers is that in our CAD/CAM package, we can assign the tool steel material to this structure. We can select this other geometry and assign the copper material to it. And then we can simply superimpose them in space. And the 3D printing machine or the additive manufacturing machine will then deposit the requisite material in these regions. So each material section will require its own submodel to allow the assignment of parameters and materials. And on the right here, we also have a pie chart distribution showing the instances of reported usage of the common CAD/CAM packages such as Abacus, SolidWorks, ANSYS, MATLAB Console, and so on. Here we also have a design flowchart for the discrete element modeling and computational fluid dynamics coupled modeling framework for multi-track, multi-layer, multi-material laser powder bed fusion. So a very complicated phenomenon to model, but it has been achieved. So first we achieve the, or we first we input the powder distribution as ascertained by experimental means. Here it is done by a master size 3000 machine, and this is input to the discrete element modeling, or discrete element model, which then lays out the first layer of powder. Then the powder data is transferred to the for phase initialization with MATLAB and some user-defined functions or UDFs. Then we perform our computational fluid dynamics calculation to figure out the transient temperature distributions, the flow of material, and so on. Then the final free surface is tracked and calculated. That final free surface is again output as an STL file, which goes as an input to the direct discrete element model, and on top of which the second layer of the powders is deposited. Again, we perform the computational fluid dynamics calculations to find the distribution of the flow field and the thermal field. The powder surface output is given again, and this continues iteratively until we have built the whole part. So among the processes commonly used for multi-metal additive manufacturing, the data energy deposition in terms of using the powder feedstock with a laser heat source, or a wire feedstock with electron beam and electric heat source compared to powder bed fusion using the powder as feedstock using laser and electron beams are the energy sources. And in terms of the speed, we see that the powder bed fusion is better. However, the duct energy deposition offers far larger build sizes, and the surface roughness of certain DAD processes may be comparable to the powder bed fusion, as well as the post-processing effort required for the DAD post-processing required for the powder bed fusion is much less in certain DAD-based processes such as wire arc additive manufacturing, or in electric arc based deposition. The surface processing is often essential. Here is a process modeling chart for the additive processes. Here we see that the volumetric energy density may be affected by certain parameters such as the layer thickness, the laser beam power, the scanning speed, as well as the hatching distance or spot size. Again, the preheating temperature is an important factor to be considered. The scanning strategy, which can either be some island line scanning or it can have some inter-layer rotation. The environment which is used, whether it is using a shielding gas, if yes, what is the composition, what is the flow rate, the powder or the feedstock characteristics itself in terms of shape and size distribution, the surface chemistry. And we also know that for wire feedstock, if the feedstock itself has defective surfaces or some elemental uptake or gas uptake in the feedstock state, these defects will also translate to poorer surface finish in the as deposited state. Then the certain uh, phenomena such as the gas porosity or the lack of fusion porosity, the texture or the preferred crystallographic direction, the grain size and the grain shape, the lattice strains, the phases, the amount of precipitates, the intermetallic phases, as well as the abrasive particles generated are decided. Again, a combination of these will finally define the material properties such as the ductility, the tensile strength, the yield strength, the abrasive resistance or the abrasiveness, and also the thermal conductivity. So this is a process design chart for the entire additive process. We see how many variables there are and how many need to be controlled. And all of these have to be fine-tuned in order to achieve the final objective in terms of the desirable mechanical properties. So the post-processing for multi-material additive manufacturing actually differs from that of mono-material additive manufacturing in the sense that the thermal post-processing, say the temperature and other parameters such as dwell time have to be adjusted considering the thermal properties of both the materials. So some sort of optimize or middle of the road parameters have to be used. Again, the commercially available post-processing technologies can manage components printed using homogeneous material designed with limited complexity and realized only using a single material for the entire component. For fully functional parts, a novel system has to be developed for post-processing, and these aspects must be considered at the design stage itself to minimize the requirement for this null value addition process. Some of the other challenges associated with the multi-material additive manufacturing are firstly the alloy compatibility. And here we see that, say, for a partner material for titanium, if we evaluate some of the other commonly available engineering alloys, such as austenitic stainless steel, martensitic and precipitation hardened stainless steel, low alloy steels, or other nickel-based, aluminum-based, or copper-based alloys, we see that when used in conjunction or as a partner for titanium, certain defects may arise, such as the formation of intermetallics, which is written as IM and color coded as red here, and some thermal property mismatches, which may also include the melting temperature mismatch in the coefficient of thermal expansion, which can lead to residual stresses, the thermal conductivity mismatch. The overall effect of all of this would be the stress concentration of the joint interface, accelerated creep, the stress corrosion cracking, as well as the high temperature fatigue. Similarly, when we are combining it with some other steels or some other nickel-based alloys, again we have the formation of intermetallic particles, which will lead to the cracks, segregation, porosity, and brittleness. So we see that the metallurgical compatibility has to be taken into account before we can actually propose material combinations. And often it might not be possible to simply print the combination of any two materials with each other. Already the set of materials which are printable by such techniques, such as ducted energy deposition, is very limited. And out of that, combining any two or more of these will again have further constraints. The second challenge is actually the dilution of composition. So usually we would have a designed composition which is very well defined in these mathematical steps. So say I have designed the composition for nickel to vary along this ramp-like function along the length or the distance along the sample. And for titanium, I want it to vary in this other step-like function. However, we see that the actual curve for variation of titanium, though initially very accurate, later starts to show certain variations, and after a point is simply unacceptably erroneous compared to my design. Similarly is the case for titanium. So actually the control over the material composition is not very sharp or not very accurate. And this dilution, which is often quantified in terms of, say, ratio of the area of the substrate to the area of the total clad in substrate, or in terms of the height of the diluted region to the combined height of the bead and the melt pool, has to be taken into account. Again, the very fundamental question of how to vary the process parameters along the composition of the material gradient is in itself a question that remains to be satisfactorily answered. I mean, will the process parameters which are optimized for one material be constant for the other material as well? Or will we have some sort of a rule of mixture type formulation for optimized parameters of the two materials? Or is there some other guiding principle? Because often we find that the properties of the materials are vastly different. For instance, for the liquidus temperature of stainless steel, it's around 1733 Kelvin, whereas for titanium, it is some 200 Kelvin higher. Similarly, for the solidus temperature, and this situation is even further complicated when the temperature dependent properties are introduced into the mix, such as the thermal conductivity. We see that may be a function of the temperature up to second power, and the specific heat may be a function of the temperature up to the third power also. So how do we actually vary the process parameters to account for the optimum deposition of all of these materials? The second thing is the lack of design guidelines in terms of either the material compatibility, which one is compatible with the other, or what are the optimal ways of distributing the material to achieve the final intended application or the intended mechanical properties is simply missing. Then the to describe the material on top of the geometric information itself is a challenge. Like we saw, one of the ways to sidestep it is to actually divide my model into a finite number of submodels, each of which to each of which I will assign a different material as well as the process parameters. However, this is still involves a lot of work, and assigning of the material deposition or the deposition properties as well as the material properties directly to subparts of a model is still limited to a very few number of packages. One of those I know is Autodesk Monolith. However, despite these challenges, we must develop these functionally graded materials because of the applications, especially in the very demanding or extreme conditions for which they are very well suited and will are expected to far outperform the parts made out of monolithic materials. And to achieve such, say, progress, the development of novel fabrication strategies, such as the toolpath planning, the design optimization, or the topological optimization, the variable process parameters, and the supportless printing have to be adequately explored. The novel material system and alloys for multi-metal AM has to be taken into account. The development of novel AM techniques itself to enhance the material mixing or to refine the microstructure have to be taken up, such as the ultrasonication assisted AM, where we use ultrasonic energy to actually break the dendrites and make the microstructure finer, as well as to improve the material mixing inside the melt pool. And then, of course, the development of physics-based and data-driven models to eliminate the need for trial and error and a large number of experiments, and rather to allow the creation of a framework which will be able to predict the material performance and properties. And of course, the logical step up from a multi-metal additive manufacturing process is the processing or production of the functionally graded materials, where you have the continuous gradation of parts, material or composition along a part. So here we see uh, the FGMs made out of copper and steel, and this has been performed by Indian researchers working with Dr. C.P. Paul at RRCAT in Indore. So some very interesting uh, research as well as topics of actual industrial relevance and application. So with this, I would like to end this bonus session for the fundamentals of additive manufacturing technologies. Even though nobody is online, I would keep this session on for some time longer in case someone joins in and has questions. Otherwise, thank you. I'm really grateful for this opportunity of getting associated with NPTEL and with Professor Sajin Kapil for conducting the live sessions of his course. It has been a good learning experience for me, where I learned both from the contents of the slides and the lectures, as well as from the participants, as they had certain very intriguing questions. And in certain instances, they also helped me with my calculations. And I also look forward to such opportunities in the future. So, thank you. The floor is open. So we will end the session now. Thank you. With that, we come to the conclusion of the live sessions for the fundamentals of additive manufacturing technologies. This is Sourav Goswami from the Department of Mechanical Engineering at IIT Bombay. Thanks everyone who has tuned in during these sessions, and I look forward to again interacting with you in the future. Thank you.